And the third talk is also by Professor Wang, also on aerosol effect on cloud and precipitation and climate. You'll be talking about the past results and future planning, right?
Okay, thank you, JP. I'm going to give you a brief summary about what we have been doing the last few years with regard to this topic, and also talking about a new initiative in terms of both observational and modeling study of this. I've been working with JP for, probably 15 years, and on a variety of topics. And in the last few years, we started working on the aerosol cloud radiation interactions. We get into some of the precipitation aspect of it, but not as much as on just the aerosol cloud radiation issues. And then we realized that when you want to study the aerosol cloud climate interaction, that's a different ballgame. You really have to involve a global model, making longer term integration, just like Wang Chen mentioned. So about 3 years ago, we started working with Professor Wu Guoxiong's group, and because he has a group working on the global climate model development and impact studies, so we migrate into that aspect. And so I'm going to give you a few examples of what we have done in that collaborations, and then move into a new initiative which we just started off earlier this year. This is a project funded by the China Ministry of Science and Technology, 科技部, 中国科技部. It's a big project. University of Maryland's Professor Li Zanqing is the chief scientist for this project. Basically is to take new measurements, over China. And there's a background there. In 2008, U.S. Department of Energy moved a mobile facility into China near Souxian, to take some measurements relevant to the aerosol cloud interaction, try to address some of the aerosol precipitation connection there. So this big project, they usually call that 973 project, will be for the 5 years, and then the heavy focus will be on taking the aircraft, ground-based and LiDARs, and also using some of the satellite measurements to look at collectively what's happening on the aerosol clouds. Of course, the purpose, one is to in combination with with models to understand aerosol cloud radiation precipitation linkage, in terms of the sequential connection there, and of course try to see whether the climate model can catch some of the linkage and for the further improvement. So the idea here is to take a new measurements together with the arm site, the mobile facility measurement in China for several months, using the longer term data sets for these two purposes. Now, I'm going to talk first on this aerosol climate effect of East Asia, and then I will wrap up my talk talking about some of our plans in terms of modeling and also the measurements in terms of try to address these two objectives. Now, to look at aerosol climate effect over East Asia, we have been working with JP, like I said earlier, using a regional model, and he's expert we just figured out a acronets this morning. What should be the statistic numeric aerosol cloud skin snacks? We debate about whether we have a K there or not. But we'll finally say there's a C there, and we don't have to worry about the K. So basically, this is a 2-moment skins for the cloud droplets. I think he's developing a 3 moments for the aerosol module. So we have been using this 2-moment skins to look at aerosol cloud interactions from a radiation aspect of it. Basically, we published a paper in quality journals to look at the aerosol impacts on the cloud microphysics and related properties, and then try to conduct some sensitivity to see how the different mechanisms plays. And then we published a paper in 2010 to look at for frontal systems in terms of mixed phase clouds, how the aerosol affect the cloud microphysics and also the precipitation. Of course, those are just sensitivity, okay? Using some of the partial observational data. Now, the key findings coming from this two study has been that find out more aerosols produce more smaller cloud droplets and more cloud water, which pretty consistent with most of the studies in terms for the warm clouds. Okay. And then secondly, not for the giant CCNs, basically the precipitation being depressed if you have more aerosols. Okay. So those are just some of the regional models process studies try to unravel some of the linkage interactions between the different dealing with aerosol and the cloud droplets. And then, of course, about 3 years ago, we starting to look into whether we can implement this SNACs into the global model, which Professor Wu is very interested in. I think the East Asia summer monsoon, East Asia climate is a very interesting regional phenomena to look at some of the aerosol cloud precipitation interactions. And so we began getting to that. It's not an easy task as what we originally anticipated. And basically, Professor Wu sent a postdoc to my place, and then he literally spent 2 years trying to work on the variety aspect of the models. The first one we did is to make a complete overhaul of the read property of the aerosols in the global models. And we have a paper dealing with sulfates, and now we have complete black carbons, organic dust, and sea salts and nitrate. You know, the nitrate is has an increasing trend in China, although the sulfates may be coming down. Okay, that's a very interesting scientific problem there. So we have we have a paper dealing with that, and then, but basically those are just mechanical. Okay, you get hold of read properties of different aerosols and then implement into the model and look at how large the impact of that on the radiation budget. So it's very, very mechanical. And then we thought about maybe some kind of fun to use this aerosol data sets in a global model domain to look at the radiative forcing concerning the aerosol direct effect, indirect effect. The direct effect, of course, is quite straightforward. You put the aerosol mass in there, you can calculate radiation perturbations. For the indirect effect, because we still don't have this SNAC scheme into the global model, even we're doing it right now. Okay, maybe some fun to look at the indirect effect using an empirical scheme, which if you know the aerosol mass, you can sort of using some empirical approach to link that to the aerosol numbers and the cloud drop numbers. Okay, and then you can sort of do a radiative forcing calculation to give you an indication about some of the effect impact of that. Personally, I'm not a fan of the radiative forcing, okay, because for the aerosols, for the tropospheric ozone is highly regional. There's a very large interannual or even seasonal contrast there. Radiative forcing, the regional forcing is much larger than the global mean or hemispheric mean. But people have been doing that. We said, well, since we put the aerosol in there, it might be fun to take a look at how the forcing compared to other forcings. So what I'm going to tell you is just a simple exercise. Before that, of course, we spend a lot of time trying to implement this SNACs into the IAP global models. This effort is still continue going on. We anticipate we're probably going to do that in the next couple of years before we get into the model observational comparison. Now, so for this second part I'm going to show you is we take we get hold of the NCAR CMIP-5's 150 years or 250 years simulations. They have they use a surface emissions and continue to update that, and then going through the photochemistry and then calculate this aerosol loading in the atmosphere. Okay, so we get hold of that and look at the decadal, including look at the different months of decadal evolution of the aerosol radiated forcing. What I'm trying to get to is to show you some of the results, but just highlight the point I want to make. This paper this is a data set is included in this paper published by the NCAR group. What they have shown is in the 1855. Basically, this is decadal mean. Okay, so you have the January, July, and then the annual mean. Basically, this is the aerosol loading in the atmosphere. Okay. Now, if you look at the different decades, 1985, 1995, and also the 2005 and 2035, because this is for the IPCC, they're doing some sort of assessment. So you can look at some of the spatial characteristics of the different loading. First of all, you look at it. There's a hemispheric asymmetry. Okay, of course, most of the sources are in the northern hemisphere land area. Okay, so you have a northern hemisphere, southern hemisphere. That's the global mean. So there's a hemispheric contrast. Okay, and primarily from three regions: the North Americans and Europe, and also the East Asia. Although the South Asia is coming up, the Indian and the Arabian Peninsula is coming up in terms of their emission contributions. This gives you a timeline of the atmospheric aerosol loading. Okay, for the Europe, for the Western Europe, for the North American, and this is for the East Asia and the South Asia. Okay, so the point here is the loading has a time evolution involved. Okay, it's not like you're going to increase all the northern hemisphere land area is going to increase. There's a time delay there, and of course beyond the 2010, basically they're based upon some sort of economic development and try to mimic some of the aerosol loading in the atmosphere. So this is a data set which we can use to look at the different. Again, I'm showing you only the sulfate. Okay, they also have the black carbon distributions, organic aerosols, nitrate not much. Basically, this is the NCAR group. They take whatever emission data they have as a function of time, and then do a chemical transport model simulations. I ask a question: how about the evolution of the aerosol loading in the atmosphere? So before we can involve some of the aerosol models in the global climate models, we basically use this data set with certain, they have a time and also the spatial distribution. So the climate model can use that as a way to look at the direct effect and indirect effect. Now, very quickly, what I'll show you is the direct effect. Basically, we look at it. This is pre-industry. This is 1980s decade minus pre-industry, and this is 2000s decades versus 1980s decade. So the point down here is, if you look at TOA radiated forcing, during this period of time, of course, aerosol is providing a cooling effect. Okay, but since the North America and Europe, they impose a restriction on SO2 emissions, or there's some other concerns, so the aerosol loading has been decreasing. So the decrease of the emissions actually decrease the aerosol loadings, which create a sort of a warming effect. Okay, so you really have to look at different period and different location in terms of what happened to the aerosol loading in the atmosphere and what's the subsequent effect. Now, another point I think Wang Qian also made, if you look at the TOA and partition the TOA into the atmosphere and also the surface, it gives you a different perspective. Okay, the black carbons and also other organic aerosols, their single scalar albedo is not very close to 1, so they're highly absorbing. So in a way, you cannot just simply look at the TOA forcing. Okay, if you look at this cancellation effect, you have a very large warming in the atmosphere and a very large cooling in the surface. Basically, it's aerosol loading cools the surface, increases atmosphere, and if you look at a different period, they are give you a different perspective. So from a climate point of view, this is our decadal simulations. So from a climate point of view, you really have to account for those different vertical structure, cooling, heating, in order to accommodate some of the direct and indirect effect. Here's just the direct effect. For the indirect effect, we use, like I said, we use an empirical approach, basically to look at the cloud albedo effect. And what we're seeing is we're getting a cloud albedo effect about 0.65 cooling, watts per meter cooling, and we have a cooling here. So those are pretty consistent with other model simulations. Okay. So we have gone through this exercise and try to find out whether we are doing a reasonable job in terms of the radiative forcing compared to other simulations. I think that our ultimate goal is to implement the SNACS, the two-moment scheme, into the global model. Okay. And further down the line, of course, you like to simulate aerosol rather than using the prescribed aerosol. Okay. So that's why the chemistry also comes in. It's a very, very big job in terms to do that more consistently and also integrate longer term. So the rest of time I will give you a very, so the point here is for the aerosol forcing, it's not uniform, both time-wise, spatial-wise. So you really have to, using a global model to look at some of the climate effect. Next, I will just go over very quickly this new initiative. This project is very large, involved probably a dozen or so institutions in China, primarily in China, and quite a few PIs from the US. But the US PI is not supported by this project. They have their own project. Okay. And this new money is primarily to provide the infrastructure support and also the new measurements. So they're invested a lot of money into the new measurements program. Okay. But basically, there will be aircraft measurements. Okay. As we know that one of the aspects we're asking is the below cloud, the CCN distributions. In terms, the cloud is not homogeneous vertically. Okay. And we know that. So cloud top, you can see from the satellite information, but the cloud top information will be different from in the cloud-based information. And also the aerosol near the cloud base. That's why we really need to have a three-dimensional, especially the vertical structure of that. So there will be aircraft measurements, and then there will be, this is concerning the aerosol and CCN, this aspect of it. And this aspect is concerning the clouds, and some of the dynamic aspect affect the clouds. And in the middle, basically, we have cloud resolving model, we have single column model, and also the global climate model. Of course, we are inserting a regional climate models aspect in between so that we can bridge the measurements and also the model simulations. Okay. And of course, we'll be using the long-term surface measurements like the ARM 2008 data sets and also the satellite data set information. Ultimately, we like to understand the mechanisms and also like to see whether the model can be used for the impact and effect studies. So this project is a very large engagement, and we'll be working on this in the next 5 years, and hopefully we'll get funded. We probably can continue for another 5 years. But I think part of this is to train the young scientists in the meantime. Okay, so my last slides will be just to give you a rundown on what we'll be doing. Basically, at SUNY Albany, we'll be working on the regional model for some of the evaluation process. the snack evaluation and the process studies. And of course, we'll be working with JP's group on continuing updating cloud skins. And then the Peking University is involved in the large eddy simulation in terms of cloud microphysics. University of North Dakota, this PI there, Professor Gong, will be working on the single column model for the diagnostic purpose. Of course, Sanqing Li, University of Maryland, will be coordinating all the measurement data sets so that we can link up with all the modeling community. Ultimately, we'll be try to use all those different approaches to evaluate the global model and what's the impact of aerosols. Okay, so I'll stop here and then thank you very much.
Okay, thank you. Questions?
So I can still have 2 minutes.
You have 5 minutes for questions. No questions? So clear? Okay. Wei-Chyung.
So there's been an argument about the reason behind this so-called accelerating warming up to 1980s. So some suggestion that that's due to the reduction of the aerosol. Are your results showing a similar thing, or what's your opinion?
I'm starting to think in that direction now. Okay. So when you would do the observation and the model or observation analysis, try to study the attributes. Okay. And of course, you try to look at the different signals versus the global warming signals caused by greenhouse gases. The greenhouse gases, atmospheric warming, surface warming. Okay. But for the aerosol, it's different. Atmospheric warming, surface cooling. Okay. If you look at only as I mentioned, only the TOA, radiative forcing, you don't see that vertical structure changes. And to make things worse is you have a different timeline of the warming versus the cooling. Okay. So, but again, I think we're just using the radiative forcing as an indicator. You still have to look at the climate response by running the full couple model in order to answer your questions.
No more questions? Okay, then thank Professor Wang.